The first talk is whole refinements for type and example-driven synthesis, and the talk is given by Niek. So, yeah.
Yes. All right. Hello, everyone. Yeah, thank you for introducing me. I'm Niek Mulleners from Utrecht University, and I'll be presenting whole refinements for type and example-driven synthesis. This joint work with my supervisors, Johan Jeuring and Wouter Swierstra. What do we mean by whole refinements? Well, you can imagine a programmer starting to write a simple program, and they might start with a type signature and some assertions or input-output examples. And then we have a start of a program. You see this circle with a 1 in it, we call it a whole. This is the starting point of the program, and which you will continue from. And it would be nice if the compiler could help you along when writing a program, because you've given all this information about what you want the program to do, so why does the compiler not tell you what to do, right? And this often happens. For example, in Haskell, you get these suggestions based on the type of your whole. So it infers that the whole has a certain type, and then you get a bunch of suggestions. And this is really nice, except that in this case, the function skip that we want to define should just remove the first element of a list. And most of these functions really don't do that. So how can we find the ones that actually match the input-output examples? So with a bit of work and some equational reasoning, we can go through all of these suggestions and remove most of them. So first, for example, reverse is a full implementation already, like it doesn't introduce any new wholes. So if you would suggest reverse, it would just evaluate to the wrong output, because it reverses the list and it doesn't remove the first element. That's very easy, but then a bit more complicated is with map that introduces a whole. You can already evaluate partially the skip function implemented as map, and then you get a list with holes in it, but we can already see that the list has 3 elements because map retains the list length, and the expected output should have length 2. So again, we can discard this suggestion. Now it gets a bit more interesting. So the const function just ignores the second argument. So we ignore the input of the skip function. And if we use some equational reasoning, we see that now skip 1 to 3 should be equal to just this whole that we've introduced. But we also know that this should be equal to the list containing 2 and 3. So now we get this constraint at the bottom. The whole 2 should have type list of A, and it should be equal to the list 2, 3. But this is not possible because we cannot just come up magically with a value of type A. So we cannot just introduce these 2 and 3. So we call these magic outputs. And we can use this to say that the constraint on whole 2 is not feasible. And therefore, we can discard this suggestion. OK? Filter is a bit similar. Here we have to do a little bit of reasoning. We can say that in order for the filter apply to the list 1 to 3 to return the list 2, 3, 1 should be mapped to false, and 2 and 3 should be mapped to true. Right? But once again, this whole has a polymorphic type. And so we cannot just create any values of type A, but we can also not inspect the values of type A. So we cannot distinguish between the values 1, 2, and 3, and thus the output cannot be different for different inputs. So again, we can say this is infeasible, and filter is not a valid suggestion. Now, for fold R, it's a bit more complicated because we're dealing with recursion. First, I'm going to look at the 2 input-output examples that we started with. And the second one, we're going to rewrite. Because since the values of the monomorphic instantiations, like these 4 and 5, they might as well be any other values, right? Because we cannot inspect them, we cannot produce them. All we know is that skip takes the like a 4 and a 5 and returns a 5, but this 5 must have been passed around from the first list to the second. And similarly, we can deduce that then skip applied to 2, 3 should return the singleton list 3. Right? And now we'll do some equational reasoning again. First we introduced the fold R, and then we evaluate fold R once, we inline it. And then we know that fold R applied to the list 2, 3 is equal to skip applied to 2, 3, as that is the refinement that we're currently looking at. And then we can use the input-output example that we found, that skip 2, 3 should be equal to the singleton list 3. And then we get the following constraint at the bottom. And once again, we can see that there is a magic output here, because this 2 cannot come from anywhere. So essentially what happened is that the skip function returns, it drops the first element of a list. And to define something in terms of fold R, we have to define it in terms of the recursive call on the tail of that list. So that we throw away the second element of the list, which we actually need to compute the skip function. I hope that's clear. OK, so all of the suggestions so far can be discarded. And then we come to pattern matching. And we can actually always pattern match. We cannot find a contradiction in a pattern match as long as the variable that we're pattern matching on is actually an algebraic data type, right? And so what we can see is that now we have found one valid suggestion, and following that we can compute the next suggestions, and these actually give the implementation of the skip function. Now, this is not the most interesting function, so you're probably not super impressed. But of course, we can do a bit more later. But first, let's look at this general pattern, right? We use equational reasoning to isolate the constraints that are on the holes. And then we compute the feasibility of these holes by taking parametricity into account. So that's where we really want to see how the types interact with the input-output examples. And this brings us to the first part of my work, the textsc reasoner. It's a type and example-based inferencer. And what it pretty much does is it computes a normal form for input-output examples that are also constrained by a polymorphic type. So this input-output example that we saw before, we can say, like, it doesn't just constrain the input list 1, 2, 3, but it actually constrains any input list that has 3 elements. And here is a formula for this that exactly describes the input outputs that are constrained by this pair of input output and polymorphic type, right? So to see a bit how that works, like we can, for example, also have ambiguity in the input. When the input list contains 2 ones, then we say, well, for all x and y, there exists z, which is either x or y, such that skip x, y returns the singleton list z. And we can use this to also find conflicts in a pair of input-output examples and a polymorphic type. So here we can see increment function, which is defined for some polymorphic type A, which is not really possible because we cannot just increment any value. And so we see that this magic output that we saw before, the 3 in the output list, is represented by this empty constraint, like z should be in the empty set, right? And the dotted line around this result shows that it's incorrect, infeasible. What we can also do is to find a bit more complicated conflicts. So once again, we have a function with a too general type, because max should have some ORT constraint to compare the elements. And if we compute the polymorphic example constraints, we get that max x, y should both return y and x. And I hope it's clear that that will it's easy to find a contradiction here. Right. What we can also do is a form of program extraction, because like I said, like we can generalize these input-output examples to some normal form, but in the end what we're looking for is the perfect generalization in a sense of these input-output examples, namely a function implementing them. But we can find a partial function implementing them by just taking those polymorphic constraints and turning them into a simple pattern match. And then at the end, we just say, well, we don't know what to return for any other output. But at least this shows that we can find a partial implementation that satisfies all the input-output examples, and thus the input-outputs are not contradicting each other, right? But this also will become useful later. Yeah, one more thing that I wanted to talk about, like we saw max without the ORT constraint, so how can we deal with the ORT constraint? So what we essentially do is we introduce another function, max prime, that replaces the ORT constraint with an ordering argument, which is either less than, equal to, or greater than. And then the compare function, which uses up the ORT constraint and turns it into an ordering, basically. We can get a max prime, which is a fully polymorphic function, so not ad hoc polymorphic anymore. And then textsc can reason about this and see that these constraints are actually not contradictory. And in practice, we don't have to do all this stuff. We can just, this just happens automatically, and we get some sort of if constraints within our polymorphic example constraints, right? So now we can reason about a lot of different pairs of input-output examples and polymorphic types, or ad hoc polymorphic types. And now we want to do something more, right? Like we already saw a hint of this before, like if we have this skip function and we know that this is a valid refinement and we have some new suggestions, we pretty much wrote the function for the programmer, right? And we can go a bit further and actually do this, like we just pick the suggestions for the programmer, essentially. And this turns it into a program synthesizer. So here's the function nub, which removes all the duplicates from a list. So it needs some equality constraint, and then we have a bunch of assertions on how it should behave. It's not so important what exactly those are, but what driver does, which is the synthesizer that we've defined, is it just generates a bunch of refinements that get the right program. And the interesting part here is that every refinement that it finds, so every whole refinement that we see here, is actually the first valid refinement the driver tries. All the other one that it tries, it can immediately discard. So this is actually just not only a correct program, but it's the very first program that we find. Now, how does that work? For example, for the first hole, we have a list of possible refinements, and first we try to just return the variable axis, or introduce nil, or cons, a map, or filter, and those all don't work, but then fold R is the first one that actually works. And then below that we have pattern matching, which is never tried because we saw already that fold R works. And we can go through the whole list of refinements. So for the next hole, we have a slightly different context, so we have slightly different refinements. But again, the first two fail, and then cons is the first one that matches, and it's actually what we want. Again, for the next case, a bit easier. For hole 4, we just find that the variable x has the right input-output behavior. And then again, we try a bunch of different refinements, and this time we see that filter already works, so we don't have to try fold R. And finally, the most interesting part is where example coverage checking kicks in. As we saw before, we were able to extract a partial program, but this is in terms of pattern matching, and we can check if all the cases are covered. And in this case, the program that is being extracted is actually a total program. And this is very easy to check, so we know that we are done with synthesis. So what we can see here on the left is like, it's maybe a bit funny to read, but we have some x and y that are in scope, and if x is equal to 1 and y is equal to 2, then we expect the whole to be true. And if x is 1 and y is 1, then we expect it to be false. And as such, the polymorphic example constraint covers all possible combinations of x and y that we can observe. Okay. And then in the end, we get this result, and driver returns this implementation, which is valid, but it is a bit cheating in a way, because we had all these refinements, and it was very convenient that always the first one that matches was actually the one that we are interested in. So the question then arises, like, who decides which refinements we can have? Who decides in which order they are tried? And well, we can leave it up to the synthesizer to pick something nice, but we can also decide ourselves. And that's why driver is based on a tactic language. And these tactics are very simple. They pretty much just usually introduce a function. So, for example, we have the intro map, intro filter, intro fold, etc. that just introduce this function and apply it to a variable in scope and do all the necessary work, like eta-expanding holes and all that stuff, in generating new, fresh variable names. And then we can compose them. We say, like, the eliminate tactic just tries one of those eliminators, and then the step tactic tries to introduce a variable or a constructor or eliminate, and then the synthesis tactic just repeats this step and just repeatedly fills holes with the same tactic. But you can imagine that there's many different tactics that would apply, and in a way this creates like a interactive synthesizer. Now, it's not very clear here yet which refinements get tried first, right? We just say this one, or that one, etc. And we want a bit more control there. So we have a biased choice constructor. So for example, the variable, once we introduce a variable, if it works, right? We don't have to try anything else, because it doesn't introduce any new holes. So actually, any refinement that doesn't introduce holes, we can use this biased choice operator to just ignore all other refinements that we would try. But the interesting ones are the ones where we do introduce holes. But we can do what we call branch control, which is where if we try map, and we know that map is a valid refinement, then we also know that fold is a valid refinement, because we can re-implement map using fold. So if map succeeded, then why would we try fold? It would only re-implement map. And kind of the same for pattern matching. Filter is different, but if map succeeds, then we know that filter will not succeed. So we also don't have to try it. There is, of course, the case where both map and filter would succeed, but then you just have the identity on lists, and that would already have been caught by the intro var refinement. Okay, but then still, we don't know, like, do we introduce a constructor first or an eliminator? And for that, we have a weighted search. So in fact, all these refinements have a weight assigned to them. We can choose whatever we want, but typically it's we don't want to introduce too many eliminators, so we give them slightly higher weight than, for example, constructors. Okay, and yeah, all this together brings us to some benchmark. We have a synthesizer, and we want to try to see, like, how well does it perform. But essentially, it's very hard to compare this directly to existing synthesizers, because they usually don't really focus on this specific form of synthesis where the user is involved with tactics. So we just try to see how these different techniques that we implemented, how they improve the synthesis. So we have a basic synthesizer that just uses, like, input-output examples to check if the to discard incorrect programs, and it's based on the types. But the feasibility specifically here is about, like, introducing this parametricity constraint, because this is what we do that previous synthesizers have not really done. And we see a very slight improvement of like 10% when we use this feasibility. And there's one example where it's like 3.6 times as fast, but it's not very impressive. And the reason is that it just doesn't occur very often that the parametricity really plays a big role in the synthesis. However, when we have this feasibility, this unlocks other kinds of analyses like the coverage checking that we saw and the branching control. And these individually also have some speed ups, and even combined they they can have a speed of almost 5 times. And in some cases, much more. And what you really see in the benchmarks is that there's just specific cases where, for example, coverage checking works really well. And this is particularly the case when we have ORT and equality constraints, because a lot of small decisions that might have to be made at the later stage of synthesis can just be shortcut, and we can just find a correct solution immediately. And branching control works particularly well for functions that would actually use something like filter or map in addition to fold R. And this is because what branching control really does is if we can define all those functions in terms of fold R, but filter and map are more efficient, and we will more likely find a solution faster. But we can actually add those to the synthesis procedure without any overhead, because we only have to check one of them every time. Right? So the cases where we actually use filter and map, this leads to a big speed up, and in other cases it might have some benefit. Right? Right, that brings us to the overview. So we have some types and examples and tactics, and those all are passed to the driver, and driver interacts with textsc to make sure that all the intermediate programs are correct, or at least don't contradict the types and examples. And this returns a program tree with some weights on it in which we can search for programs. And that's pretty much it. Do you have any questions?
We have 10 minutes or so. So, any questions? Yes.
I have 3 questions. Choose any which one. I have 3 questions. Choose any which one. Thank you for the talk. Yeah. First one is, could you eliminate the parametricity you have here, that you exploit here, by unit types without equality? So a number of different unit types, which would capture part of the parametricity you're exploiting here. And the second question is, like, why are you using filter, map, and then fold R, and then case, since the latter case would consume all of them if you at least if you also have function composition in there as a pattern for inferring. And the third question is, have you compared this to let's say Claude Code, and see what that one gives you? Thank you.
Let's see, I'm not sure if I understand your first question exactly. Is that
so instead of having for all alpha, list alpha to list alpha, you have just list of a particular unit type. You need multiple ones for every type variable. You need one, just a unit type without equality, and going to list of unit type, right? And then the examples would actually also be just 1, 2, 3 would be mapped to unit element.
I think this sounds a bit like there's this paper on parametricity where like property-based testing is made easier by using specific types and citations, right? In some cases you could do that, right? You could have like a simpler type, but the whole point is that we want the user to provide monomorphic input-output examples that use integers, for example, and then see how those match, how the inputs actually are passed to the output. So if you would turn it into units, then you would sort of lose this connection, I would think. But maybe I'm missing a bit the point. We could talk about it later. The other question I remember, let's see. Yeah, you said, why would this case be here? That's it.
Why would you have the first 3 cases?
Yeah, why would you have the 3?
Why not just go straight to intro case?
Yeah, because it's not the most efficient way to a correct program, right? So we know that if it can be implemented with a map, and we try to implement it with a map, it's much faster. And pattern matching always would work, but it tends to lead to overfitting, especially because we start with few input-output examples. You could just start pattern matching, and in the end, there's no examples anymore, and That's it. So the whole point is that we saw this program extraction where we turn the input-output example into a program, and this essentially does a bunch of pattern matching. But the interesting part is generalizing beyond the examples in a natural way, and that's where these combinators are formed.
And did you try Claude Code or anything like that?
Right, yeah, they definitely outperform what we do. Yeah, the only thing that makes it interesting to me is that we have guarantees of correctness, right? We can show that these refinements actually make sense and lead to a solution. And if we have a bunch of refinements, we can say, like, these are the refinements that would work and these are the refinements that would not work. Whereas Claude just generates stuff. And yeah, you can test that those are actually what you want. But let's say you have a program that's very complex, and we just want one small next step for the user to pick from, because these synthesizers generate just a bunch of things, and you can look through them and find the one that you want. But sometimes it's nice to just know this one step brings me closer to something. And then maybe Claude could pick up again and give a correct implementation. Yeah.
Yeah. Any other questions? Yeah. Yes.
So when you're generating the examples with the ordering and equality, do you have to? How does that work? Like, how do you know which equalities and inequalities matter and which ones don't?
So let's see. This part, you mean, right? Well, we pretty much say all of them are relevant. In this case, we only have 2 inputs, so we just say we use the compare function and add it to it. What we do, this is not what we actually do. What we actually do is just take all the inputs and create like how do you say that? A set of equivalence classes. And in the case of OR constraint, these are ordered equivalence classes, and equality constraints, it's just equivalence classes. And then we use that as an additional input to this helper function. Yeah.
So does that mean it works? Does that mean that this is only working specifically on EQ and ORD and not on any arbitrary type class?
Yes, exactly. Yeah. You can imagine, for example, monoid, if you would have this is something that I didn't really go into that much, but we need our types to be strictly positive for this to work. Because if you have an input argument from like A to A, then you can apply it many times and you wouldn't really know whether it would eventually lead to the output that we want or not. And so many, these constraints can usually just be replaced by the functions in the dictionary that they represent. And for ORD and equality, we can turn them into something that's strictly positive. And for other constraints, that's harder or impossible. Yeah.
Are you saying that you can handle arbitrary or strictly positive ones?
Sorry?
So his question is about whether you can handle only ORD or EQ or not. But your answer seems to say that arbitrary, strictly positive ones are okay.
Yes, yes. But most constraints do other stuff that's more complicated than that are not strictly positive anymore. Or like even if the function that the constraint implements is strictly positive itself, once you put it into this function signature, the whole thing is not strictly positive anymore. So yeah, that's essentially.
Okay, thank you.
Yeah.
Yes, yes. Please wait for asking a question because this is being recorded.
Does this work with higher order functions, synthesizing higher order functions? It kind of looks like it should. And if it does, why replace with compare xy and not just compare? So if I wanted to synthesize, if I wanted to pass in a function here and use that in my synthesis, does that work?
As a part of the function that you're synthesizing,
Yes.
You want a higher order
Yes.
function? Yeah. No, that does not work.
Okay. Is there a fundamental reason, or does it just not work in your implementation?
So if you have some, the thing is just that you can synthesize programs like that. You just cannot get any additional reasoning like that, so you didn't really explore it. Because if you have a function in scope that just turns an A into an A, and it could be anything, then you cannot do any of this reasoning where you show that an output cannot come from the input, because there could be an arbitrary amount of applications of this function that you're passing. So there, yeah, you could have it as long as the function that you're passing returns, for example, a Boolean or an ordering or something like that, something finite. But if it's something like A to A, that doesn't work.
I see. Thanks.
Yeah.
We have 2 or 3 minutes. If I can ask some silly question, what is the most complicated example you have succeeded? Well,
oh yeah, not super spectacular, but let's see, something like sorting, like it can implement.
You mean what kind
like
of sorting?
List sort, and yeah. I think that's probably the most complicated. Yeah.
Okay, thank you.
So yeah, it's not groundbreaking, but it's more about these small refinement steps that lead you to this solution.
So we can gradually develop our programs using your tool. So it's implemented, and we can use it.
Yes, but then again, it's a very specific setting with very specific types, specific ways in which you can define your input-output examples, and specific refinements that are possible. So I don't know of any languages currently that it would perfectly fit into. Maybe like the Hazel programming language would be a nice way to introduce these things, because they have already some of these things implemented. I know that polymorphism was added recently. So this would be a nice place to actually use it in practice. But yeah, you can use the system and synthesize programs with it.
Well, I'm sorry to ask too many questions, but if I am a user of your system, well, maybe writing the tactics would be very difficult for me. Well, maybe.
Possibly, yeah. So that's why there are like existing tactics that you can use and just explore the programs that it generates. But yeah, writing the tactics would be a bit more complicated. And it would be nice to have some interface there to make this easier. Yeah.
Okay, thank you very much. Thanks again.
Thank you.